name is Antonio Fortunato and I am Deputy Head of Crew Operations for the European Astronaut Center in Cologne. The topic of this lesson is the International Space Station. As a vehicle, we will discuss its modules, its main capabilities, and to a lesser extent, its operations. Now, a very interesting module, a smaller one, that is attached to Node 3 is the cupola. Also, the cupola is a European contribution to the ISS program. The cupola is the porch of the ISS. It provides a beautiful view of the planet. This is one of the favorite places for the astronauts. This is where astronauts perform, for instance, Earth observation activities. You see here Samantha Cristoforetti during her last mission taking pictures of the Earth from space. But the cupola is also important because it hosts the main robotic workstation. Now, in the past, when there was no cupola, the robotic workstation was in the US lab. And this was okay because the astronauts could have situational awareness of what the robotic arm was doing simply by looking at the camera feeds. Of course, if you can complement what you see in the camera feeds with a direct eye contact, with a direct line of sight view of the robotic arm, this is even better, and that's why now the robotic workstation is installed inside cupola. One final module that is installed to Node 3 is Beam. This is really the latest addition to the ISS stack. Beam is an inflatable module designed and built by Beagle Aerospace. And the concept that we're trying to prove here is that it is possible to fly to space modules in a very compact shape and then inflate them in space and make available a much larger space for the astronauts. You see here the inflation sequence of Beam. On the top left, you have Beam in its fully packed configuration, and then you see how it slowly becomes bigger and bigger till it assumes its final fully extended configuration. Now, there is really nothing in Beam right now. Beam is a demonstrator. It is there to show that we can effectively inflate a module in space and that we can keep this module in space for a long time. One of the things that is really being tested is the resistance of the external hull of the wall of the module. Normally the hatch to Beam is closed, and once a month an inspection is performed to see that everything is okay and to collect some important data about the inside of this module. You see here a nice picture of the crew that actually supervised the inflation of Beam. If we move forward, we exit Node 3, we exit Node 1, we move to the US lab. Well, if the service module was the heart of the Russian segment, the US lab is really the heart, the main component of the US segment. This is the US lab as it was taken out of the cargo bay of the shuttle and installed on the ISS. And this is the way the US lab looks on the inside. The US lab hosts important pieces of equipment, important computers. There are lots of systems. I mentioned before that Node 3 has many systems dealing with regenerative life support system. Well, some of those systems are duplicated, and they are also present in the US lab. So for instance, the oxygen generation assembly and the carbon dioxide removal assembly, they are in Node 3, but also in the US lab. The US lab, however, does not just deal with systems. It also deals with payloads. It deals with equipment that is used to perform science. And you see here one such piece of equipment. This is the Microgravity Science Glovebox, or MSG. The MSG is the largest glovebox available on the space station, but it can also be used for providing basic services to experiments that do not necessarily require the containment of a glovebox. And you see here Paolo Nespoli during his last mission working on one such experiment. Also, the US lab hosts some exercise equipment. Here you see Alexander Gerst exercising on the cycloergometer. It is known as CIVIS. One important point to make here: there are different types of exercise equipments on the ISS, and they are in general all isolated with the vibration isolation system from the rest of the ISS structure. And this is because most of the time we want to perform science in a clean microgravity environment. We want to perform science with an environment that is as close as possible to true zero-G. And obviously this wouldn't be possible if we had astronauts exercising with equipment that was directly connected to the structure of the space station. That is why there is a vibration isolation system for all the exercise equipment. You see it very clearly here. It's the metal frame with the interconnection to the rack. And this is also why the most sensitive experiments to disturbances to the microgravity environment, they are also usually provided with the vibration isolation system. Also, interesting enough, you have here a stationary bike, a cycloergometer without a saddle, and that is because it really doesn't work in zero-G. It was tested during Skylab to have a cycloergometer, a stationary bike with the saddle, but the crew of Skylab very quickly realized that this saddle was more of a hindrance than a help. All right, moving out of the US lab, we have yet another interconnecting node. This is node 2. Node 2 is a European contribution to the ISS. It was built in Europe, and again, it is an interconnecting node. So it provides attachment points for other modules, and in the case of node 2, it does provide attachment points for visiting vehicles. We have seen that on the Russian side, the service module, docking compartment 1, MRM1, and MRM2 can be used to dock Progress and Soyuz vehicles. Now, what about the vehicles that are operated by the other international partners? Well, those vehicles are berthed to node 1. So especially the Zenit and Nadir positions are normally used for Dragon, Cygnus, and HTV. Now you see here in the picture there is also a different docking port on the forward side of node 2. This is one of the pressurized mating adapters. This is really an adapter to allow a vehicle with a different docking port than the common berthing mechanism that is used by Cygnus, ATV, and Dragon to dock to the ISS. It is in fact a converter from the common berthing mechanism to the androgynous peripheral attachment system that was used on the space shuttle. Just very recently, an additional adapter has been added on top of the PMA to allow future manned vehicle to dock to the forward port of Node 2. And we are hoping that in the 2018 timeframe, we will see the Boeing CST-100 and the SpaceX manned Dragon dock to exactly that port. Now, what is special about Node 2 is that it hosts the crew quarters. It hosts the sleeping compartments of the ISS crew. We have seen before that 2 sleeping compartments are in the service module. Well, we have a permanent crew of 6 people, so we need 6 crew quarters, and the additional 4 crew quarters are in Node 2. Those are small compartments. They're about the size of telephone booths, but they do provide privacy to the astronauts. They do provide a certain level of noise, isolation, and quiet environment for the crew. Interesting enough, in the crew quarters, there are also laptops that allow the astronauts to connect to the internet. It's the so-called crew support LAN. It's not exactly a direct connection to the internet. This would be far too risky from an IT security standpoint, but by clever methods, it is possible for the astronauts to connect to the internet from the ISS, and those computers are normally located in the crew quarters. Now, Node 2 is also important because it serves as the attachment point for the European module and for the Japanese module. The European module is attached to the starboard side of the Node 2, and it is really the main contribution of Europe to the ISS program. This module has not been just built in Europe, but it is also operated by a European control center, the Columbus Control Center in Munich. You see here in the picture Hans Schlegel during the installation of Columbus in February of 2008. This is how Columbus looks like from the inside. Columbus is really a laboratory. It is a module dedicated to experiments in science and technology. There is equipment that can be used for experiments in plant biology. There is equipment that can be used or has been used in the past, for instance, for protein crystallization experiments. But first and foremost, Columbus is an important module for human life science experiments. We have equipment that allows the astronaut to perform investigations that make use of electrocardiogram, electroencephalogram. We can perform echography, and we can centrifuge blood samples. And you see here an example of one such experiment. During his last mission, Paolo Nespoli was to perform an experiment where his electroencephalogram was taken while he was performing cognitive tasks on a laptop. As mentioned, we are also able to perform echography. This is important not just for science, but also for operational medicine reasons. Now, as Europe has its own module, also Japan has its own module. It is a module built in Japan and operated by a control center in Tsukuba. The Japanese module is really made of 3 major parts. We have a major pressurized module called JPM. We have a logistics module, really a stowage closet called JLP. And then we have an external platform that allows us to perform, for instance, experiments that require materials to be exposed to the space environment. Now, what is really unique about the Japanese module is the capability to easily ferry equipment outside without any need to have astronauts going EVA. There is an airlock, and this airlock can be loaded with equipment. Then the internal door is closed, the external is open, and the Japanese robotic arm can take this equipment out and either install it on the external platform or simply operate it from the robotic arm. One example of equipment that is operated directly on the robotic arm is the Cubesat Releaser. This is really interesting. CubeSats can be loaded into a release device, and then the robotic arm takes it, orients it in the right direction, and the CubeSats are sent to space. Also, the Japanese module is used for different scientific experiments, and it has a number of important systems. For instance, the Japanese module has an experimental communication system in the Ka band, and this is a feature that is really unique of this module. Also, the GEM is a fairly large and fairly tidy module that is normally used for public relation events, and you see here one of such examples in the picture. The International Space Station obviously represents the present of human spaceflight. It is the single largest program that was ever endeavored in this field, and a number of very important investigations both in science and technology are being performed on the ISS every day. What I really hope to see in the future is using the experience that has been gathered on the ISS to develop an infrastructure in space. We don't want anymore to perform missions where we visit other planets. We perform a number of important activities and then we come back, never to continue our exploration for 20, 30, 40 years. To allow a sustainable exploration of the solar system, to further our human presence in the solar system, we really need to develop an infrastructure that we can use to have our presence in space be as sustainable and as operational as possible. We need communication infrastructure, we need an cargo transportation infrastructure, we need a number of basic services that are available right now for low Earth orbit, but obviously need to be expanded to allow, for instance, construction of a permanent base on the moon, or astronauts to visit and eventually colonize Mars.